Hi, this is a review term paper presentation on the topic superconductivity in neutron stars. I am Ankit Yadav, fourth year student from Department of Physical Sciences, ISR Mohali. This is the outline of my presentation. I will shortly review the formation of neutron star and their interior. After that, I will present the idea of superconductivity in neutron stars, how and when the Cooper pair forms in the neutron star, which lead to the superconductivity in neutron stars. Okay, what are the observational evidences to verify the theory? After that, I will conclude my presentation. Okay, let's start from the formation of neutron star. When a massive star runs out of the fuel and the gravitational pressure exceeds the radiation pressure and gaseous pressure of stars, it leads to the imploding of star and supernova explosion happens. This explosion led to the formation of neutron star composed of iron 56 core. Because of the iron 56, the most stable nuclei as predicted by the nuclear physics standard model. Neutron stars are usually 1.5 to 20 solar masses and have the radius around 10 to 15 kilometers. And this property makes them the one of the most dense object in the universe, except black holes. Okay, let's review the interior of neutron star. A neutron star is found from the supernova explosion. It has the atmosphere composed of hydrogen, helium, and carbon. As one goes deeper in the neutron star, density of star increases dramatically due to the gravitational pressure. When the density reaches around 10 to power 7 kilogram per meter cube, atoms will be completely ionized and reaching to this pressure need going to few deeper in the neutron star. Going few centimeter deeper led to the density around 10 to power 10 kilogram per meter cube, which is enormous. It led to the increase in the number density, and we know that Fermi energy is directly proportional to number density power 2 by 3, and thus Fermi energy also increases. By the time when Fermi energy reaches approximately 10 to 6 electron volts, iron 56 will no longer be the stable nuclei. Protons and electrons will combine to form neutrons, and standard model predicts the formation of nuclei when with the neutrons having magic numbers. Okay. The more deeper one goes in, the more the neutron density increases. At the end, krypton 118 is expected to be the most stable nuclei. However, at this time, when density reaches approximately 4.3 into and 10 for 14 kilogram per meter cube, the nuclei becomes so neutron rich that neutrons become to drift out of the nuclei, and one is a lattice of exotic nuclei embedded in a sea of neutrons. This is the similar condition as the electron gas in the metal. When the density crosses 2.5, approximately 2.5 into 10 to the power 17 kilogram per meter cube, or nuclear saturation density, a nuclei will melt and will form a fluid of electron, proton, and neutrons. Going deeper will lead to the much higher density, and at this point, the exact prediction of core component cannot be made. Yet. It may happen that baryons will decompose and the quark gluons will be formed. However, we don't have the enough evidence yet to predict the center of neutron star. Now, let's review the idea of superconductivity of neutron stars. For the superconductivity to happen, it needs extremely low temperature on Earth, but how the idea of superconductivity arises at such high temperature in neutron star? The mystery of superconductivity was resolved in 1957 by Bardeen, Cooper, and Schiffer, known as Bish's theory of superconductivity. According to Bish's theory of superconductivity, the result of superconductivity is the result of condensation of Cooper pairs, and the formation of Cooper pair needs attractive interaction potential. This condition is fulfilled for the protons in the inner core of the neutron star, as they are attracted by a strong forces, because the attractive interaction potential, a strong attractive interaction potential, critical temperature of the neutron for the protons have the value approximately 10 to the power 10 Kelvin. The core of neutron has the temperature around 10 to the power 8 Kelvin. Neutron star has the temperature around 10 to the power 8 Kelvin. It leads to the suitable condition for superconductivity for the protons, and while having the temperature less than the critical temperature. Okay. There will be no superconductivity because of the very weak interaction potential between electrons. For electrons. Okay. But Misner effect explains that the superconductors expel the magnetic field, and we know that a magnetic neutron star have very high magnetic field, approximately 10 to the power 15, 10 to the power 12 to 10 to the power 15 Gauss. Then how the superconductivity is expected to happen in the neutron star? This problem can be resolved by the understanding of the effect of magnetic field on the superconductors. There are two types of superconductor named as based on the property of based on their properties in the corresponding to the magnetic field. Okay, they are type 1 and type 2 superconductors. As the superconductivity cancel the magnetic field by developing magnetization, or in other words, they become the perfectly diamagnetic when temperature of the superconductor is less than the critical temperature, which is indeed the case for the neutron stars in the inner core. For type 1 superconductors, there exists a critical magnetic field below which they expel the magnetic field and remain superconductive. And once the critical magnetic field is crossed, when the value of critical magnetic field is crossed, they no longer remain the superconductive, or they return in the normal state. But for the type 2 superconductors, there exist two critical magnetic fields for superconductors. Below the first critical magnetic field, superconductors follow the Meissner effect and expel the magnetic field lines, but in between the first and second critical magnetic field, superconductors forms vortexes or magnetic flux tubes and allow the passage of magnetic field through the quantized flux tubes. Based on this concept, scientists speculated that neutron stars should have type 2 superconductivity, but there has been research going on which claims that type 1 superconductivity is also possible in neutron stars. The immediate question arises that how to verify it, how to verify the theory. There has been close observation of period of neutron star in the past, which shows that there are periodic glitches in the data, which can be explained by the current theory, according to which interaction between magnetic fluxes and the vortices of superfluidity of neutron stars causes the periodic glitches in the neutron stars. Okay, thank you.